In our physical world, it is desirable for objects to perform actions as part of their purpose. There are laws which govern the movement of these objects and methods for combining objects together to achieve the required motion. The combination of these objects is known as a mechanism. Machines are devices which are used to perform these actions over and over again, being designed to handle the forces that they are commonly subject to.
The forces of nature govern all the motion around us. The most easily demonstrable force is that of gravity. A ball dropped from a position high above the ground accelerates until its motion is changed by hitting the ground. The force of gravity on a particular object is measured by its weight, using devices especially designed for the purpose. It should be noted that the force of gravity varies at different places on the Earth and depending on the proximity of other masses such as the Moon. In outer space, the force of gravity is negligible compared to the frame of reference of the capsule a person is contained within. Besides motion towards a large body, motion is achieved by an object being in contact with another object. The combination of forces works to produce the speed and direction of an object. When an external force acts on a stationary object, it starts to move. The object changes its motion and direction depending on the new force that is applied. This change in motion is an acceleration of the object proportional to the size of the force and inversely proportional to the mass of the body. When an object is stationary, it means that all the forces cancel each other out. Two spring balancers pointing in opposite directions, when pulled with both hands, produce equal forces. A similar result can be achieved by attaching one end to a wall. This practical is also demonstrated with a weight pulling on a pulley. When an object is attached to a fixed point, known as a fulcrum or pivot, a turning effect occurs based on the force applied. This is known as a moment, and the magnitude of a moment is also known as torque. A force acting on the movable part of the object can be resolved into two components at right angles to each other. Length can also be resolved into two components similarly. The torque can be calculated either by multiplying the distance from the pivot to the position at which the force is applied and the component of the force that is in the direction the object is moving, or by multiplying the full force by a component of the distance from the pivot to the applied force point called the moment arm. The moment arm is perpendicular to the line of action, an extension line in the direction that force is applied. The simplest machine making use of a fulcrum is the lever. Examples of levers in use include doors attached to hinges, bicycle pedals, rake handles, removing lids from tins, and seesaws. A very practical example of a lever in use with gravity is a balance. It is found that weights of the same mass suspended at equal length away from the pivot will cause the balance to be in equilibrium, with neither side accelerating towards the ground. If the weights are unequal, this is exactly what happens. It is often convenient to balance a large weight with a smaller weight, in which case the smaller weight is placed further away on the other side of the pivot. To start the balance moving from either side, extra effort must be applied. In the case that one side with a weight resistance must be lifted, effort must be made to the other side. A ratio known as the mechanical advantage compares the weights that must be used in order that the resistance side may be on the verge of lifting. The mechanical advantage is equal to the resistance divided by the effort. This mechanical advantage changes depending on the position of the resistance and the effort applied. Besides this kind of lever, of which the resistance is on the opposite side to the effort, there are another two classes of lever where the resistance and effort are on the same side of the arm leading away from the fulcrum. Levers of the second class have the effort applied further away from the fulcrum than the resistance, whereas levers of the third class have the effort applied closer to the fulcrum than the resistance. All kinds of levers use a torque equation to equate the effects of both the resistance and effort. The resistance multiplied with the distance from the resistance to the fulcrum is equal to the effort multiplied by the distance from the effort to the fulcrum. Whenever a larger weight is lifted with a comparably smaller effort, it is found that the weight has not been lifted as far as the distance the effort has been applied for. Wheels are special types of levers. The wheel revolves around its axle, which acts as a fulcrum. Placing two wheels together, the force of resistance and effort are balanced depending on the weights and radii of the wheels on which they are placed. Pulleys are single wheels that act as levers. When pulling up a weight, the same distance of the applied effort is required when pulling the rope. The velocity of the resistance is the same as that of the effort rope, so the velocity ratio is 1. A pulley fixed to the ceiling is called a fixed pulley. This device may have two weights of different amount connected to each end, called an Atwood's machine, to measure gravity. If a rope is directly connected to the ceiling and a pulley is connected to the weight, effort is required in an upwards direction, the same way the resistance moves. Twice as much rope length is required to lift the load a certain height, because the pulley has two sides, and the rope length on the fixed rope side is moved over to the other side of the pulley, added to the rope length required on that side to lift the load. This type of a pulley is a movable pulley, and the entire system has a velocity ratio of 2. More complex systems of fixed and movable pulleys can be added together to lift larger weights with longer lengths of rope. Fixed combinations of pulleys attached to the ceiling are known as blocks, whereas combinations of movable pulleys attached to the load are known as tackles. Together the systems are known as block and tackle. Usually they are arranged so that a rope must be pulled downwards. These systems are not ideal, and there are forces at work within them to ensure that the mechanical advantage is less than the velocity ratio. When the rope is wrapped several times around the same pulley at the block and tackle, with each end that is added, an extra length is added to the pull rope, and it is progressively easier to pull the rope up to a certain point. An inclined plane makes it easier to lift a mass to a certain height. Attaching a car to a spring balance, less force is needed to move it up the ramp at smaller slopes than greater ones. Gradually increasing the slope, finally the plane is at such a slope that it is no longer any benefit. If a plane is wrapped around in a circle, it can make it so that the height of the mass lifted is closer than that of its original position. A triangular piece of paper shows the pattern that this makes around a round rod. It has the appearance of a screw. Indeed, screws are used in jacks to lift heavy loads such as cars. Bolts and nuts are made to fit each other, and the parts of the nut and bolt can be used to squeeze together two different objects so that they don't fall apart. There are special types of tools to work with nuts and bolts called spanners. Screws require screwdrivers to fit into their fixings. An adjustable wrench or shifter makes use of a screw to adjust the distance apart of its jaws, much like a vise or clamp. Special measurement devices, such as micrometers, equate the number of turns around a screw to the distance apart of their jaws for measurement. Another form of basic machine is the wedge, which acts to drive two surfaces apart. A screw will do this when it is screwed into some wood, but a more basic form is a door wedge. Such wedges are also used to prop up tables with uneven legs, creating the necessary height with a certain amount of the wedge underneath the leg. An axe is an example of a tool that uses a wedge to split wood. A crowbar can be used to pry apart hard-to-budge objects such as flywheels. Wedges are double-inclined planes.
These basic machines offer examples of labour-saving effects that enable the operator to perform difficult tasks with comparable ease. In each case, the movable parts must be designed so that they can operate under the stresses that the loads that they move will require. Constructing these systems can take a considerable amount of time, but the advantages of time saved by repeated use ensures that these machines will have their place in any well-designed workshop.